Welcome to the deep dive. For the past couple of years, a lot of the buzz in AI, it's really been about the engine itself, these incredible large language models.
Right, the raw power has been impressive.
Totally. But I think we're seeing a shift now. We're moving past just marveling at the engine. Now it's about building the whole car around it, something reliable, something high performance.
Exactly. We're talking about the move from just generating plausible text to building truly autonomous agentic systems.
And that's a big leap. It needs structure, right? Blueprints.
That's precisely it. Agentic design patterns. That's what these blueprints are. And when we say agentic system, what we mean is basically a system that can sense its environment, make decisions based on its goals, and then act on its own.
But that autonomy, it sounds great, but it must bring a ton of complexity.
Oh, absolutely. Huge complexity. How does it manage its state? How does it use tools reliably? How do you make it resilient if something goes wrong? Patterns exist to tackle exactly these kinds of challenges.
Okay, so that's our mission for this deep dive. We want to give you the essential toolkit, break down these core design patterns, the ones that are really battle-tested.
Yep. Well, look at what they do. The why behind them, maybe some of the trade-offs involved.
And show how they actually enable these sophisticated AI behaviors. We'll touch on frameworks too, things like LangChain, LangGraph, Crew AI, Google's ADK. They're kind of the canvas these patterns get painted on.
Right. We're aiming to simplify this whole stack for you. So let's kick things off with maybe the most fundamental part. How these agents decide what to do next and how they check their own homework, so to speak.
All right, first up, the routing pattern. I like thinking of this as the agent's sort of central nervous system.
Yeah, that's a good analogy. It introduces conditional logic, so instead of just marching straight ahead on one fixed path.
It can actually make choices. It can look at a situation and decide, okay, do I go left or right? It lets the agent handle different kinds of inputs or situations dynamically.
It's basically triage. You need this because the real world isn't neat and tidy. Think about a customer service bot.
Right.
It gets an incoming message. It can't just do the same thing every time. It needs to route. Is this person asking about their order status? Okay, I need to call that API. Is it technical support? Right. Pull out the diagnostic tool.
Or maybe it's something complex that needs a human. Escalation.
Exactly. Routing allows that split-second decision based on what the user said or maybe what happened in the previous step.
And there are different ways to actually do this routing,
Yeah.
right? It's not just one method.
No, definitely not. And there are trade-offs, like you mentioned, usually around speed, cost, and flexibility. We see kind of three main approaches.
Okay, what's the first one?
The most straightforward and often the starting point is LLM-based routing. You literally just ask the language model.
Ah, so you prompt it like, based on this query, should I call the API, query the database, or summarize?
Pretty much. You prompt it to output a specific category word, maybe apical or summarize, or sometimes a structured JSON object. The system then reads that output and follows that path.
The big advantage there must be flexibility. The LLM can understand nuance,
Totally. It can handle things it hasn't seen before. But the downside,
latency, and cost.
bingo. You're paying for a full LLM call just to make a decision. That can get slow and expensive fast, especially at scale.
Which probably leads to the next method,
Yeah.
something faster.
Yeah, embedding-based routing or semantic routing, this is popular when you need to handle a lot of volume.
How does that work? Embeddings, like vector representation.
Exactly. You turn the incoming query into a vector, a numerical representation of its meaning. Then you compare that vector to a set of pre-stored vectors where each stored vector represents a different route or capability.
So you find the closest match based on meaning, not just keywords.
Right. It's powerful because it captures semantics, handles nuance pretty well, but it's much, much faster than calling the LLM every time. Once you have the embeddings, the comparison is quick.
What's the catch?
Well, you need a good set of those pre-calculated route embeddings, and you need to maintain them. And if a query comes in that's totally outside the meanings you've stored, it might struggle to classify it correctly.
Okay, so LLM-based is flexible but slow. Embedding-based is faster but needs setup. Is there a third way?
Yep, the old, reliable. Rule-based routing. Simple if-else logic, keyword checks, regular expressions.
Ah, so if the input contains reset password, just send it straight to the password reset function. No interpretation needed.
Precisely. It's lightning fast, super cheap, and completely deterministic. You know exactly what will happen. Great for common, unambiguous requests.
The zero flexibility, I imagine. If the user says, I need to change my login, it might miss it.
Exactly. It breaks the moment the phrasing is different. So in practice, you often see hybrid systems. They use rules for the obvious stuff, semantic routing for the nuanced stuff, and maybe fall back to the LLM router for the really tricky, novel inputs.
That makes sense. Mix and match. And you mentioned LangGraph earlier. That framework seems built for this kind of complex routing, right?
Absolutely. Because LangGraph is based on a state machine, a graph structure where nodes represent steps and edges represent transitions, it's inherently good at managing these conditional flows, loops, and complex decision points where the state needs to be updated based on the outcome of an action before deciding the next action.
Okay, so that's decision making. What about quality control? Making sure the agent's work is actually good.
That brings us to the reflection pattern. This is like the agent's internal editor or critic. It's the ability to look at its own output or even its internal plan, evaluate it, and then correct itself.
Self-correction. That sounds powerful. How does it work?
The most common and effective model here is called the producer-critic model. You split the job into two roles.
Two agents. Or maybe two separate calls to the LLM.
Often two separate LLM calls, yeah. The producer generates the first draft, could be code, an email, a summary, whatever. Then the critic agent gets that output.
And the critic has specific instructions, like a reviewer.
Exactly. The critic is prompted with a clear rubric, or maybe a specific persona like senior code reviewer or fact checker. Its job is just to evaluate the producer's work and provide feedback.
Why separate them? Why not just ask the first agent, okay, now review your work?
That's a great question. You can try that, but it often doesn't work as well. Asking a single LLM instance to generate something and then immediately critique it, while it struggles, it tends to be biased towards its own initial answer.
Like having a bit of an ego? My first answer was great.
Kind of, yeah. It struggles to switch context effectively and spot its own flaws. Separating the roles forces a fresh look, a dedicated focus just on finding problems using that specific critical persona. You usually get much more objective and robust feedback that way.
But two LLM calls instead of one. That sounds like it doubles the latency, doubles the cost again.
It absolutely does. That's the major trade-off. You're trading speed and cost for higher quality and reliability.
So you wouldn't use this for everything.
Definitely not. You reserve it for the important stuff. Generating production code, writing legal documents, summarizing critical financial data things where mistakes are costly. For just casual chat, you'd likely skip reflection.
And how does the loop stop? Does the critic just keep giving feedback forever?
No, you define a stopping condition. The producer takes the critic's feedback, generates a revised version, and sends it back to the critic. This loop continues until the critic agent outputs a specific signal, maybe a phrase like, "Pody's perfect," or "all checks passed." That tells the system the quality bar has been met and the process can stop.
Okay, so it's an iterative refinement process driven by that separated critique. That makes sense for achieving high quality. So what happens when the task is just too big or complex, even for an agent using reflection?
Then you need more structure. You need a strategy. That leads us to the planning pattern. Think of this as the strategy architect.
So breaking down a big, hairy problem into smaller, manageable steps.
Exactly. If the request isn't just a single, simple query response, you probably need planning. Imagine asking an agent to write a comprehensive report on the future of renewable energy.
Yeah, it can't just start writing.
Right. It needs a plan.
Oh.
Step 1, identify key subtopics. Step 2, search for recent research papers using Tool A. Step 3. Search for market reports using Tool B. Step 4. Synthesize findings for each subtopic. Step 5, draft the report. Step 6, maybe run a reflection step to review the draft.
So the planning itself becomes the first task.
Often, yes. Frameworks like Crew AI really highlight this. You might have one agent whose sole job is to create the plan, maybe outputting it as a bulleted list or even a structured JSON object.
Like defining the sequence, who does what tools are needed.
Precisely. That plan then guides the execution. Forcing that planning step up front makes the LLM organize its thoughts and significantly reduces the chances of it getting lost or going off track, especially when multiple steps and tools are involved.
Okay, so planning breaks down the work. What if those different steps require different kinds of expertise or tools?
Perfect transition. That's where multi-agent collaboration comes in. Instead of trying to build one super agent that knows everything.
You build a team of specialists.
Exactly, an ensemble. It's about recognizing that a single monolithic agent often hits limits when facing tasks that cross different domains or require varied skills.
How do these specialist agents typically work together?
We see a few common structures in the sources.
Hmm.
The simplest is probably sequential handoffs. It's like an assembly line.
Agent A does its part, passes the result to Agent B, who does the next step, and so on.
Yep. Agent A researches, Agent B writes, Agent C edits. Clean pipeline.
What else?
You also have hierarchical structures. This is more like a manager and their team. There's a supervisor agent that gets the main goal.
And the supervisor breaks it down, like using the planning pattern.
Exactly. The supervisor creates the plan and then delegates the specific subtasks to specialized worker agents. Maybe one worker is great at database queries, another excels at calling external APIs, another is the code generator.
And the supervisor keeps track of the overall progress.
Right. It manages the overall state and coordinates the workers while each worker just focuses on its specific job.
And I guess the producer-critic model we talked about is also a form of collaboration.
Absolutely. It's a very specific, very powerful two-agent collaboration focused purely on quality assurance.
So the benefits of this multi-agent approach seem clear. Modularity, you can swap agents in and out.
Right. Scalability, too.
Mhm.
And robustness, if one specialized agent fails, maybe the supervisor can route the task to a backup or try a different approach instead of the whole system crashing.
Okay, makes sense. But now, if you have these different agents, maybe even built using different tools, like one is LangGraph, another is Crew AI, maybe a third is using Google's ADK, how do they actually talk to each other? How does the supervisor in LangGraph delegate a task to a worker built in Crew AI?
The Tower of Babel problem.
Yeah.
That brings us to the crucial need for inter-agent communication, and specifically, something like Google's A2A protocol.
A2A, agent to agent.
Yep. The big challenge is interoperability. If every framework has its own way of talking, you can't easily build systems that mix and match components. We need a common language, an open standard.
And A2A aims to be that standard.
That's the goal. And the fact that you see major players like Microsoft, SAP, Atlassian getting involved suggests it's gaining traction as that necessary lingua franca for agents.
So let's get into the nuts and bolts a bit. How does A2A actually enable this communication?
It defines a few core concepts. First, the core actors. You have the user, obviously. Then you have the A2A client. That's the agent making the request, like our LangGraph supervisor.
Yeah.
And then you have the A2A server, which is the remote agent receiving the request and doing the work, like our Crew AI worker. The key here is that the remote agent is a black box to the client.
Meaning the client doesn't need to know how the worker does its job, just what it can do.
Exactly. It just needs to know the interface, the capabilities, and those capabilities are defined in the agent card.
The agent card. Like a business card for the agent.
Kind of. It's a standardized JSON file that acts as the agent's digital ID. It tells you crucial things like, what's the agent's URL endpoint? What version is it? What specific task can it perform? Does it support streaming results back? What kind of authentication does it need?
So before one agent can talk to another, it checks its agent card to know how to connect and what to ask for.
Precisely. It's the standardized handshake that makes interoperability possible.
Does A2A support different kinds of interaction, like just asking a question and getting an answer back?
Yes, it supports standard synchronous communication, one request, one response, using something like a send task call. But crucially, it also supports streaming via send task subscribe.
Streaming. So getting results back piece by piece. Why is that important?
Think about long-running tasks. Generating a complex report, processing a large data set, maybe real-time code generation. You don't want to wait potentially minutes for the final result. Streaming lets the remote agent send back updates incrementally, making the system feel much more responsive.
Okay, that makes sense. Now, I've also heard about something called MCP, Model Context Protocol. How does that relate to A2A? Are they the same thing?
Good question, because it can be confusing. They're different. A2A is about the communication between different agents. It's about delegation, coordination, managing workflows across potentially different frameworks.
Okay, the higher level orchestration.
Right. MCP, on the other hand, is about how a single agent structures the information in its context window when it interacts with external tools or data sources. It's about formatting the prompt and the tool's response so the LLM can understand it reliably.
So A2A is agent-to-agent communication, while MCP is agent-to-tool communication context formatting.
That's a great way to put it. A2A manages the team, MCP manages how each player talks to their equipment.
All right, let's shift gears slightly. One of the biggest inherent limitations of LLMs is that their knowledge is frozen in time, based on their training data. Agents need to remember things and access up-to-date information. That sounds like memory management.
Absolutely crucial. For an agent to maintain context in a conversation, personalize responses, or solve problems that unfold over time, it needs memory. We usually break this down into two types, much like human memory.
Short-term and long-term.
Pretty much. Short-term memory is essentially the agent's working memory. It's the information held right there in the LLM's current context window.
So the recent back and forth messages, the results from the last tool it called, maybe the output from a reflection step.
Exactly. But the key things about the context window are, one, it's limited in size, even if getting bigger, and two, it's ephemeral.
Meaning, once the conversation or session ends, poof, it's gone.
Gone. It only serves the immediate interaction, which is why you absolutely need long-term memory or persistent memory.
This is where information sticks around between sessions.
Yes, this is knowledge stored externally outside the LLM's context window, usually in databases. Very often these days, it's vector databases.
Because they allow searching based on meaning, semantic similarity, not just keywords.
Right. This lets the agent retrieve relevant past interactions, user preferences, or learned information, even if the current query uses different wording. It's the key to continuity and personalization over time.
And managing this persistence, deciding what's temporary versus what needs to stick around, frameworks need ways to handle that. You mentioned Google's ADK.
Yeah, ADK provides a neat, explicit way to manage this using prefixes in its state dictionary. It helps developers control the scope and lifetime of data.
Prefixes, how does that work?
So, when the agent stores a piece of information in its state, the prefix you use determines how long it lasts and who can access it. If you use no prefix, it's the default, basically ephemeral, gone after the current turn or maybe session.
Okay, like short-term memory.
Right. Then you have session. Data stored with this prefix lasts for the current session ID, useful for things like items in a shopping cart during one visit.
Makes sense.
The really important one for long-term memory is user, data stored with the user. Prefix persists across all sessions for that specific user ID. This is where you'd keep user preferences, past conversation summaries, things you want the agent to remember about that user forever.
That seems incredibly useful. You avoid asking the same questions over and over.
Exactly. It saves time, cost, and improves the user experience dramatically. Then there's app. This is for data shared across all users of the application. Think global configuration settings, shared knowledge bases, that sort of thing.
And the last one.
Temp. As the name suggests, this is for very short-lived data, only needed for the current processing turn, maybe within a single React loop. It gets deleted immediately after. Good for temporary calculations or intermediate results you don't need to keep.
So those prefixes give developers fine-grained control over the memory's scope and persistence. Very practical.
Yeah, it's a good illustration of how you manage the trade-offs between the expensive, limited context window and cheaper, persistent external storage.
Okay, that external storage, especially for knowledge, leads us directly into probably one of the most talked about patterns, RAG, or retrieval augmented generation.
Ah, yes, RAGL. It's become fundamental. It's the primary way we overcome that static, outdated knowledge problem of base LLMs. It lets the agent access and use external, current, often domain-specific information.
Can you walk us through the basic RAG process?
Sure, it's typically a three-step process. Step 1, retrieval. The system takes the user query, analyzes it, and searches an external knowledge base, could be documents, database records, website content for relevant snippets of information, often called chunks.
And that search is usually semantic, right? Using embeddings again.
Very often, yes. To find chunks that are relevant in meaning. Step 2, augmentation. The system takes the most relevant retrieved chunks and literally stuffs them into the prompt that is preparing for the LLM, along with the original query.
So you're giving the LLM the question and the potential answer of relevant facts right there on the prompt.
Exactly. Step 3, generation. The LLM receives this augmented prompt, the query, plus the retrieved context, and uses that information to generate its final response. The idea is that the response is now grounded in the provided facts, making it much more accurate and verifiable.
That basic RAG process has been hugely impactful, but I hear talk now about agentic RAG. Is that something different?
It is. It's an evolution, making RAG smarter and more reliable. Think of standard RAG as just retrieving and stuffing. Agentic RAG introduces a reasoning layer and agent that actively works with the retrieval process.
How so? What does this agent do?
Instead of just passively accepting whatever the retriever finds, the agent might perform several reasoning steps. For example, it might look at the initial query and think, this is ambiguous. Let me generate 3 different search queries to try and cover the possibilities.
Okay, so it's more strategic about the retrieval itself.
Right. Or, once chunks are retrieved, The agent might actively interrogate them. It could check for contradictions. Does chunk A conflict with chunk B? It might assess relevance. Is this chunk really answering this specific question?
Almost like applying the reflection pattern to the retrieved information.
That's a great way to think about it. It might even make a separate LLM call specifically to score the retrieved chunks for quality or relevance before deciding which ones to include in the final prompt for the generator LLM.
So it's adding a layer of critical evaluation and refinement to the retrieval process itself.
Exactly. It acts as a gatekeeper, ensuring that only high-quality, relevant, non-contradictory information makes it into the final generation context. This significantly boosts the reliability of the final answer, which is crucial when you absolutely cannot afford hallucinations or incorrect information.
Okay, let's move into how these agents actually think and how we can make them more efficient and safe. Starting with reasoning techniques. The simplest one seems to be chain of thought.
Yeah, COTI was a foundational insight. It's simply prompting the model to think step by step or show its work before giving the final answer.
How does that help?
It forces the LLM to break down complex problems, math problems, logical reasoning, multi-step planning into smaller, intermediate steps. This explicit decomposition often leads to a more accurate final result, and it also gives us visibility into how the model arrived at the answer. Makes it less of a black box.
So it improves accuracy and transparency, but it's still just internal reasoning, right?
Yeah.
What about interacting with the world?
That's where REACT comes in. REACT stands for reasoning and acting. It's probably the core loop you see in most functional agent systems today.
Does as it were.
It interleaves the internal reasoning, the thought step, similar to COCOT, with external actions and observations. So the loop looks like thought, action, observation, thought, action, observation.
Okay, so the agent thinks about what to do, thought. Then it performs an action, like calling a tool or an API, action.
Right. Then it gets a result back from that tool, observation. And crucially, it feeds that observation back into its next thought step.
Ah, so it can adjust its plan based on what actually happened in the environment.
Exactly. If it tries to call a tool and gets an error back, observation, its next thought can be, okay, that didn't work. Let me try a different tool or approach. It makes the agent adaptive to real-time feedback, much more robust than a purely pre-planned chain of thought approach.
But again, trade-offs. Each turn of that thought-action-observation loop takes time, right?
Yeah.
More back and forth.
Definitely. React is more adaptive, but likely slower than a COT plan that just executes straight through. You're trading some speed for that dynamic adaptability.
This idea of giving the model time to think, did that relate to performance generally?
It does. There's a concept called the scaling inference law. The basic idea is that for many tasks, an LLM's performance gets predictably better the more computational resources, essentially, more inference time you give it for a single query.
So letting it think longer makes it think better.
In many cases, yes. For an agent, this might mean allowing it to explore more possibilities during its thought step, maybe running multiple reasoning paths in parallel before choosing one, or simply performing more thorough analysis before taking an action.
It's like telling the agent, don't just give me the first answer that comes to mind. Take a second. Be deliberate.
Precisely. That deliberate pause, that extra computation allocated to reasoning, often significantly improves the quality and reliability of the agent's autonomous actions. It reduces the chance of errors or suboptimal choices.
Okay, but if we're doing multiple LLM calls for routing, reflection, reasoning, and maybe giving them more inference time, the costs could really add up, especially if we're always using the biggest, most powerful model.
Huge cost implications, which leads directly to the need for resource-aware optimization. You can't just throw your most expensive model like Gemini Pro or GPT-4 at every single incoming request. That's incredibly inefficient.
So how do you optimize?
You build intelligence into the system to allocate resources based on the actual complexity of the task. A common pattern uses another layer of routing.
A router agent specifically for choosing the model.
Exactly. A lightweight router agent first classifies the incoming query's complexity. If it's something simple, like a basic factual lookup or a simple rephrasing.
Send it to a cheaper, faster model, like Gemini Flash or Haiku.
Right. But if the router detects a complex request needing deep reasoning, multi-step analysis, or nuanced generation.
Then routed to the powerhouse model, like Gemini Pro or Opus, and accept the higher cost and latency for that specific task.
Precisely. But it doesn't stop there. How does the router know if its classifications are right?
You need feedback. Another critic.
Yep. You add a critique agent into the loop. This agent evaluates the quality of the output produced by whichever model the router chose.
So if the cheap model starts messing up tasks the router thought were simple.
The critique agent flags that poor quality. That feedback is then used to refine the router agent's logic over time. Maybe it needs to be less aggressive about sending queries to the cheap model. The system learns and self-optimizes that cost-performance balance based on real-world results.
Very cool. It tunes itself. Okay, shifting from efficiency to safety. Guardrails and safety patterns. This seems critical for agents acting autonomously.
Non-negotiable. You need layers of defense to ensure agents operate safely, ethically, and within their intended boundaries. You don't want them generating harmful content, leaking private data, or going wildly off task.
What do these layers look like?
It starts right at the beginning. Input validation and sanitization. Filter the incoming request for malicious prompts, attempts to jailbreak the model, or prohibited topics before it even hits the LLM.
Like a firewall for the agent.
Kind of, yeah. The next layer is behavioral constraints, usually baked into the main system prompt. This is where you give the agent its persona, its rules, its do's and don'ts. Very clear instructions, sometimes called defensive prompting, about what it should and should not do.
Defining its operational boundaries.
Exactly. And then, even if the input and behavior are constrained, you need output filtering. After the LLM generates a response, but before it's shown to the user or used in the next step, you scan it for toxicity, policy violations, sensitive information, etc.
So check the input, constrain the behavior, check the output.
Right. And for really critical decisions, you might need a human-in-the-loop mechanism, where the agent has to pause and get human approval before proceeding. It's a multi-layered defense.
Are there technical ways to enforce some of this, beyond just prompting?
Yes. A powerful technique is using structured output schemas. Tools like Pydantic in Python let you define exactly the format the LLM's output must conform to, say, a JSON object with specific fields and data types.
And if the LLM produces something malformed?
The validator rejects it instantly. It fails the step. This acts as a strong technical guardrail, ensuring the agent produces data in the expected format, which prevents errors cascading downstream. It enforces a kind of structural compliance.
Okay, so we have safety measures. But agents are still probabilistic. How do we know if they're actually working well over time? Traditional software tests might not be enough. That sounds like evaluation and monitoring.
Exactly right. You need continuous monitoring because performance can drift. You track the basics, the quantitative stuff, latency monitoring, how fast is it, crucial for user experience, and token usage, how much is it costing, vital for budget control.
But what about the quality of the output? That seems harder to measure automatically.
It is harder, but there are new techniques. One of the most promising is LLM as a judge.
Using another LLM to evaluate the first one. Like the critic pattern again.
Very similar, yes. You give a separate, often powerful LLM a structured prompt that includes a detailed rubric. You ask it to evaluate the primary agent's output based on specific criteria: clarity, relevance, factual accuracy, tone, lack of bias, whatever matters for that task.
And it gives a score or a qualitative assessment.
Right. It can provide nuanced, consistent, quality judgments at a scale humans just can't match. It's becoming a standard way to track qualitative performance over time.
Beyond the final output, should we look at how the agent got there?
Absolutely. That's evaluating agent trajectories. You don't just look at the final answer. You look at the sequence of steps the agent took, the thoughts, the actions, which tools did it choose, the observations.
And compare that sequence to what? An ideal path.
Yeah, you might compare it to a known good reference trajectory using metrics like exact match of steps, or maybe just checking if the key steps happened in the right order. This helps you understand why an agent might be failing or being inefficient. Maybe it's consistently choosing the wrong tool at step 3. It's debugging the reasoning process itself.
This whole focus on defining behavior, ensuring safety, measuring quality, evaluating the process, it feels like it's leading somewhere more formal.
It absolutely is. All these accountability measures are driving a significant conceptual shift, something the sources are calling the contractor model.
Contractor model. As opposed to what? A vague assistant.
Pretty much. We're moving away from just giving the AI a fuzzy, open-ended prompt and hoping for the best. The contractor model pushes towards defining a formalized contract before the agent starts working.
A contract. What would that include?
Explicit, verifiable deliverables. A clearly defined scope of work. Maybe even cost estimates or ceilings, specific execution standards or quality requirements.
So really nailing down the expectations up front.
Exactly. And it might even involve a dynamic life cycle of negotiation and feedback before execution. The agent might receive the request and respond, okay, based on your request, I propose these three subtasks. Estimated cost is X, estimated time is Y. Do you approve this contract?
Wow, so it's a negotiation before the work starts?
Right. This whole shift, clear contracts, negotiation, accountability through evaluation, transforms the AI from this unpredictable, maybe helpful assistant into a much more reliable, accountable partner or contractor. And that level of accountability is absolutely essential if we want to deploy these agents in serious, high-stakes business or scientific domains.
Okay, for our final segment, let's look at the real cutting edge, where agents go beyond just following instructions, even complex ones, and start to actually learn, explore, and discover things on their own.
Yeah, this is where things get really exciting. We're talking about agents that can proactively explore their environment, autonomously refine their own knowledge, maybe even improve their own processes.
Systems that improve themselves.
That's the idea behind self-improving systems, sometimes called SICA, for self-improving cognitive agents. These are systems designed not just to perform a task, but to run meta-level improvement loops.
Meta level, meaning they analyze their own performance.
Yes, but more than that. They analyze their performance, identify bottlenecks or flaws in their own structure or tools, and then try to generate and test modifications to improve themselves. They're essentially trying to debug and upgrade their own code or strategies without a human explicitly telling them how.
That sounds incredibly complex.
hmm
Are there real examples of this level of autonomy?
There are emerging examples. One fascinating one from the research is Google's Co-Scientist project. It's a multi-agent system specifically designed to mimic and automate the scientific discovery process.
Automating science. How does that work? What kind of agents are involved?
It's a whole team, like we discussed earlier. You have generation agents that propose novel hypotheses based on existing knowledge. You have reflection agents that critique these hypotheses, checking them against data.
Okay, standard producer-critic stuff.
But then it gets more advanced. They have ranking agents that use an ELO rating system, like in chess, to make different hypotheses compete against each other, identifying the most promising ones.
Using ELO for scientific theories. That's clever. It forces the best ideas to rise to the top.
Exactly. Then evolution agents take the top-ranked theories and try to refine or combine them. There are also agents focused on experimental design and even meta-review agents overseeing the whole process.
So what did this co-scientist system actually achieve?
The results were pretty stunning. They tasked it with researching a specific area of bacterial genetics, mobile genetic elements. The system autonomously explored, hypothesized, ranked, and evolved its theory. It generated a novel top-ranked hypothesis about how certain elements, CFPACIs, interact with phage tails to broaden their host range. This finding was later validated experimentally.
Okay.
Here's the kicker. That same discovery had taken an independent group of human researchers over 10 years of dedicated lab work to uncover. The co-scientist system reached a similar conclusion through its autonomous process in about 2 days.
10 years compressed into 2 days. That's unbelievable.
It really highlights the potential of these autonomous discovery systems. Another key example pushing this boundary is AlphaVolve.
What does AlphaVol do?
It's an AI agent designed to discover and optimize algorithms themselves. It cleverly combines LLMs with evolutionary algorithms.
How did that combination work?
The LLM acts as the creative source, proposing high-level algorithmic ideas or strategies expressed in natural language or pseudocode. Then the evolutionary algorithms take over, translating those ideas into concrete code and running millions of tiny variations, mutations, and tests to find the most efficient low-level implementation.
So the LLM provides the creative spark, and the evolutionary part does the massive brute force optimization.
Kind of, yeah. The LLM guides the search in promising directions, and it's not just theoretical, it's delivering real-world results.
Like,
The sources mention AlphaVolve has already led to measurable efficiency improvements, like optimizing sorting algorithms, resulting in things like a 0.7% reduction in Google's global compute resource usage for certain tasks, and optimizing low-level GPU instructions by up to 32.5%.
wow, those aren't trivial games when you're operating at Google scale.
Not at all. These agents aren't just writing summaries anymore. They're making fundamental discoveries in science and engineering that have immediate, tangible impacts on efficiency and resource use.
It really feels like these frontier systems, co-scientist, AlphaVolve, they're the culmination of all the patterns we discussed. They must use planning, reflection, multi-agent structures, everything to achieve that level of autonomous learning and discovery.
Absolutely. They represent the convergence, showing what becomes possible when you architect these systems effectively using these foundational blueprints.
Wow, okay. That was quite the tour through the agentic blueprint. We really covered a lot of ground.
We did. We went from the basic decisions, routing, and reflection, all the way through structuring the work with planning and multi-agent teams.
Grounding them in reality with memory and agentic hierarchy, ensuring control with optimization and guardrails.
Establishing accountability with evaluation and the contractor model, and finally touching on that incredible frontier of autonomous learning and discovery.
And I think the big takeaway for me is that these patterns, reflection, planning, react, A2A for communication, they aren't just nice to haves. They
Yeah.
seem essential. They're what actually transforms these powerful but sometimes flaky LLMs into systems you can potentially rely on.
That's exactly it. They are the architectural building blocks for reliability and autonomy.
And you mentioned accountability, particularly with the contractor model. That feels like the linchpin for actually trusting these systems in the real world.
I think it is. That shift from just prompting and hoping to defining a clear contract scope, deliverables, standards, that's fundamental. When an agent can understand that contract, negotiate it potentially, perform self-critique, reflection, access its memory, use tools reliably, react, RG, and deliver verifiable results against that contract, that's when you start building real trust.
Without that trust, without that accountability, deploying these agents for anything truly important, finance, healthcare, science, it just seems too risky.
Exactly. Accountability is the price of admission for mission-critical deployment.
So maybe a final thought for our listeners, building on that contractor model idea.
Yeah, here's something to think about. Reflect on your own work, your own life. Where do you currently rely on vague requests or instructions, maybe when delegating to a team member, working with a vendor, or even using a piece of software? Now imagine replacing that vague instruction with something closer to a formalized contract. What if you explicitly defined the desired outcome, the scope, the quality standard, how you'll verify success, even just mentally outlining that contract? How much clarity and reliability could that bring, not just to AI, but potentially to your everyday human interactions and workflows?
That's a great point. Applying that discipline of the contract beyond just AI. Food for thought.
Definitely something to mull over.
Well, this has been incredibly insightful. It's clear the journey towards truly useful autonomous systems is very much an architectural one now, built on these patterns.
Indeed it is. Thanks for diving deep with me.
Thank you. And we'll see you next time for another deep dive.